Traditionally, levels of 5% or 1% are used for the critical significant values. More stringent critical values may be required when human injury or catastrophic loss of life is possible. Less stringent critical values may be preferred when there are low risks. Sometimes an issue of practical versus statistical significance may arise. In this situation, a claim is found to be statistically significant, but it may be cost prohibitive. One situation where this could occur is when an inappropriate number of samples are used to reject a null hypothesis, but on an individual basis. The significance of the result is beneath notice. This highlights the importance of power analysis to boost the validity of our hypothesis test decision. In order to truly explain sample size, effect size, and power, we must really understand the relationship between the three. Instead of giving you an explanation heavily grounded in statistical principles and mysticism, let's consider this visual scenario. Suppose we are standing a certain distance away from what appears to be an anthill. We cannot be sure, but it is possible that there are in fact two anthills. But because we are so far away and the anthills are so close to each other, we cannot be sure. We are given a set of binoculars with varying degrees of magnification. We could use the binoculars, but in some circumstances, they may not be needed. Let's define three parameters. Distance from the anthills. This is our power. As an organization, we set this value. Typically, it is 0.8. If the proximity of the two anthills were very close, we could always move closer to the anthills to make our determination. The closer we get to the anthills, the smaller the distance, and therefore the lower the power. Clearly, if we hope to demonstrate that our conclusion carries any meaningful weight and compelling results, we need to maintain our distance. In other words, we need to maintain our power and look for another solution. Proximity of the anthills. This is our effect size. The closer the anthills are to each other, the smaller the effect size, and the reverse. When we conduct a study, we do not know the effect size. We must make an assumption. It may be too liberal or too conservative. Typically, we will assume a medium effect size. Magnification setting of the binoculars. This is our sample size. This is the output. Remember that our aim is to determine with confidence whether or not there are two anthills or one anthill at the distance we are standing. We can use a tool called G-power to make this determination. The number of inputs vary and are numerous, and also include parameters for the type of statistical test we will be performing. Effect sizes are broken into ranges based on small, medium, and large. This table gives a summary of the values of various effect sizes at each level. Cohen's d is used to quantify the effect size for the difference of two means. Cohen's f is an extension of Cohen's d. We typically see this effect size when working with statistical tests that involve the f distribution. It is a ratio of two standard deviations. Cohen's h is measured distance between two proportions. Hedges g is closely related to Cohen's d. We typically lean toward Hedges g when our sample size is smaller than 20. Eta square is typically found in ANOVA statistical outputs. It is an effect size associated with the proportion of variation attributed to a specific variable out of the total. This is similar to the amount of explainable variation. Eta square is not a robust measure, though. Eta square also overestimates the explained population variance. This tendency to overestimate is diminished as the sample size increases. For smaller sample sizes, omega square is superior to eta square. Omega square is like eta square in that it measures how much variance in the response variables are accounted for by the explanatory variables. But in general, it is lesser biased because it uses unbiased measures for the variance components. Rho is used for correlation effect size. G-power is a tool to compute statistical power analyses for many different t-tests, f-tests, chi-square tests, z-tests, and some exact tests. G-power can also be used to compute effect sizes. The website to download the software is found here. There are also tutorials at the download site to show you how to use G-power. G-power is essentially an optimizer. We start with a distribution, the red curve, governed by a type of statistical test we are running, and use this to derive a non-central distribution, the blue curve, based on the original distribution. Note that the non-central distribution is optimized when the area to the left of a critical statistic based on alpha under the original distribution, the red curve, reaches beta. Recall that power is 1 minus beta. The sample size can then be determined from the non-centrality parameter, in other words, the peak-to-peak distance between the two distributions. An important dynamic in power analysis is the role of the parametric test. Using a parametric test further reduces your minimum sample size requirement. However, in the real world, it is highly likely that some of our assumptions will be violated, particularly normality. Fortunately, we have a series of useful non-parametric tests that carry with them some significant and valid functionality. When we use a non-parametric equivalent, there is a diminished amount of statistical power. Therefore, our sample sizes, when using non-parametric tests, must incrementally increase. As an example, if a Pearson correlation with a power of 0.8 requires 84 samples, this sample size would deliver a power of 0.9119 times 0.8 or 0.7295 for a Spearman correlation. To reach an equivalent power of 0.8 for Spearman, we would need to aim for a Pearson power of 0.8 divided by 0.9119 for a total of 0.8773. A power of 0.8773 requires a minimum sample of 104. Therefore, a minimum of 104 samples would be needed if we were running a Spearman correlation.